For millennia, humanity has gazed at the stars, charting constellations and mapping the visible tapestry of our night sky. Yet, what we perceive with our naked eye, or even with powerful telescopes, represents only a fraction of the cosmos. Beyond the familiar planets and their well-known companions, lies an immense, enigmatic expanse filled with countless celestial bodies, many of which remain hidden, lurking at the very edge of our detection. This journey begins with a fundamental question: what else is out there, quietly orbiting, subtly influencing, just beyond our current reach? Before we delve into the unseen, let's establish what we do know. Our solar system is a bustling neighborhood, dominated by 8 major planets. Each of these planets, in turn, can host one or more natural satellites, what we commonly refer to as moons. A moon is simply a celestial body that orbits a planet, gravitationally bound to it. Think of Earth's own moon, a familiar face in our sky, or Jupiter's Galilean moons, easily visible with binoculars. We've catalogued hundreds of these known moons, each offering clues about the formation and evolution of our solar system. But what about those objects that defy easy categorization? The scientific endeavor is fundamentally about pushing boundaries, daring to look beyond the obvious. Astronomers are not content with just what's visible, they constantly strive to perceive the obscure, to uncover the faint whispers from the deepest reaches of space. This quest requires unparalleled patience, advanced technology, and often, innovative ways of thinking. We're talking about searching for objects so small, so distant, or so dimly lit that they are essentially invisible to conventional methods. It's a cosmic game of hide and seek, where the it is an entire celestial body, waiting to be found. Finding these elusive objects presents immense challenges. Imagine trying to spot a single grain of sand from hundreds of miles away, at night, without a flashlight. That's a simplified analogy for the difficulties involved. The primary hurdles are distance, size, and illumination. Distant objects appear incredibly faint because their light has spread across vast expanses of space. Smaller objects simply reflect less light. And if an object is dark in composition, it becomes even harder to distinguish from the blackness of space. These factors combine to make direct visual confirmation extraordinarily rare for objects at the edge of our perception. When direct observation is difficult, scientists often turn to indirect methods. One of the most powerful tools in this regard is the study of gravitational perturbations. Gravity is a fundamental force, the mutual attraction between any two objects with mass. Even a small, distant moon exerts a tiny gravitational pull on its parent planet, causing minute, subtle wobbles or deviations in the planet's orbit. These tiny shifts, though incredibly difficult to measure, can act as a celestial fingerprint, hinting at the presence of an unseen companion. It's like feeling a ripple in the water, even if you can't see the pebble that caused it. The edge isn't just a physical location in space, it's also a boundary of our technological capabilities and observational techniques. It's where the signals from a celestial body become so weak, so close to the background noise of the universe or our instruments, that they are almost indistinguishable from static. Pushing past this edge requires instruments of incredible precision, capable of discerning the slightest flicker of light or the most minute gravitational tug. It demands innovative data processing to filter out interference and amplify the faint signatures of distant objects. This is where scientific ingenuity truly shines. Years of painstaking data collection and analysis often begin with subtle anomalies. Imagine observing a known planet, meticulously tracking its path. Suddenly, the data starts to show minor, inexplicable deviations, tiny irregularities that don't fit the expected orbital model. These anomalous readings are like a faint tremor, suggesting something unseen is influencing the system. For a long time, these might be dismissed as observational errors or instrumental quirks. But to a persistent scientist, they are tantalizing clues, urging further investigation. This is often the first, tentative step towards a major discovery. Following these initial hints, the real work intensifies. Scientists embark on persistent observation campaigns, dedicating countless hours, days, and even years to repeatedly monitor the target planet. This isn't a quick glance, it involves scheduling precious telescope time, coordinating international efforts, and meticulously collecting data across multiple wavelengths and instruments. The goal is to gather enough evidence to rule out random fluctuations and confirm that the anomalous readings are consistent and repeatable. It's a testament to human patience and dedication, peering into the night, waiting for the universe to reveal its secrets. Collecting vast amounts of data is only half the battle, interpreting it is the other. This often requires the development of new algorithms, sets of detailed instructions that computers follow to process and analyze data. These specialized algorithms are designed to filter out background noise, detect subtle patterns, and enhance faint signals that would be invisible to the human eye. Researchers spend years refining these computational tools, making them more sensitive, more accurate, and more efficient, systematically sifting through petabytes of information, searching for that one elusive needle in the cosmic haystack. After years of indirect clues and computational analysis, came the moment of the first visual. It wasn't a clear, crisp photograph, but a mere suggestion, a blurry, pixelated speck of light, barely distinguishable from the surrounding cosmic canvas. This initial image, though uncertain, was revolutionary. It was the first time that the gravitational whispers had been corroborated by even the faintest visual evidence. It was a whisper of light, not definitive proof, but an incredibly significant step, transforming a theoretical possibility into a tantalizingly probable reality, igniting a new wave of focused observation. In science, a single observation, no matter how exciting, is rarely enough. Every major discovery must undergo peer review, a rigorous process where other independent scientists critically evaluate the methods, data, and conclusions. This involves sharing the raw data, detailing the techniques used, and allowing other experts to attempt to replicate the findings or identify any potential flaws. This collective scrutiny is the bedrock of scientific integrity, ensuring that any claims are robust, reproducible, and truly represent a new understanding of the universe. It is a slow, methodical process, but one that builds absolute confidence in the results. And then, after years of tireless work, persistent observation, advanced algorithms, and rigorous peer review, the confirmation arrived. Clearer, more precise data, cross-referenced by multiple observatories and validated by independent teams, painted an undeniable picture. A new moon, previously hidden at the very edge of our detection capabilities, was undeniably real. This wasn't a sudden, dramatic explosion of light, but a quiet, profound revelation. The universe had subtly expanded its known boundaries. This moonlight at the edge represented not just a new celestial body, but a triumph of human ingenuity and unwavering scientific curiosity. So, what did this hidden moon reveal? Initial observations suggest it is relatively small, perhaps only a few hundred kilometers in diameter, making its detection even more remarkable. Its orbit is notably eccentric, meaning it's not perfectly circular, but rather elongated, swinging far away from its parent planet at times and closer at others. Its surface appears dark, possibly composed of primitive, carbon-rich materials, explaining why it reflects so little light. These unique characteristics are already providing fascinating clues about its violent formation and long, lonely journey through the outer reaches of the planetary system it now calls home. The discovery of this hidden moon has significant implications for planetary formation theories. Existing models largely predict the types and distributions of moons based on our observations of more visible systems. The unusual orbit and composition of this new moon challenge some of these assumptions, suggesting that the processes forming moons might be far more diverse and complex than previously imagined. Perhaps distant, colder regions of protoplanetary disks, the swirling gas and dust clouds from which planets form, can produce moons under different conditions, or perhaps gravitational interactions during a system's early history are more chaotic than we thought. This revelation compels us to redefine what we consider the edge of our cosmic understanding. It's not a fixed boundary, but a constantly shifting frontier. What was once invisible has now been brought into focus, forcing us to ask, if we found one hidden moon, how many more are out there? This discovery suggests that our solar system, and indeed other planetary systems, might harbor a wealth of smaller, fainter, and more distant objects that are yet to be found. It expands our perception of what's possible, where to look next, and inspires a new generation of scientists to develop even more sensitive instruments. The success in finding this hidden moon highlights the need for even more advanced observational techniques. Future telescopes, both ground-based and space-based, are being designed with unprecedented sensitivity and resolution. Imagine arrays of telescopes working together as one giant eye, or spacecraft equipped with advanced sensors capable of detecting the faintest thermal signatures or the most subtle gravitational ripples. These next-generation instruments promise to push the edge further still, allowing us to delve deeper into the cosmic tapestry and potentially uncover entire populations of celestial bodies we can't even conceive of today. At the heart of every discovery, from the simplest observation to the most profound revelation, lies human curiosity. It is the insatiable drive to explore, to question, to understand the universe around us. This hidden moon is a testament to that enduring spirit, a story of individuals who refused to accept the limits of what was known, who dedicated their lives to chasing faint signals and deciphering complex data. It reminds us that our universe is a boundless source of wonder, continually inviting us to look closer, to think harder, and to never stop asking what if. The revelation of this hidden moon is more than just the addition of another dot to our celestial maps. It's a powerful reminder that our universe is far richer and more intricate than we can often grasp. It underscores the vast number of unseen wonders that still await discovery, challenging us to continue our exploration with renewed vigor and imagination. This moon is just one example, a single, quiet revelation from the depths of space, hinting at countless others. It makes us pause and reflect on the boundless nature of the cosmos and our place within its grand design. Every quiet revelation, every faint flicker brought into focus, deepens our awe and expands our understanding. The journey to discover this hidden moon has been long and arduous, marked by skepticism, persistence, and ultimately, triumph. It's a story that echoes the very essence of scientific exploration, a continuous, patient unfolding of cosmic truths, one subtle clue at a time. As we conclude our exploration of Moonlight at the Edge, let us carry forward the wonder of this discovery, reminding ourselves that the universe is an endless book, with countless chapters yet to be read, and many more quiet revelations waiting to be heard.